All right, now let's have a look at question 4, and this is also taken from a past exam paper. So this question is not too difficult, but you can see that it comes down to 15 marks at the end. So it's not difficult, but there is a bit of work to do. All right, let's begin. So they say to me, the feed to a distillation column has the following analysis on a mole basis. So we spoke about distillation columns in the previous example, that's question 3, but essentially distillation is separation by boiling point. So it makes use of the fact that different components have different boiling points, and it uses this to pull a different component out at the top compared to the component at the bottom. And so just so you have a picture, you send a feed into this little tower, and out of the top of the tower comes one of your lighter components, or the component with a lower boiling point, and the component with a higher boiling point comes out at the bottom. This is the basic principle of distillation. And they tell me that this is a mole basis. Now, why do they tell me it's a mole basis? Remember, my feed to the distillation column is often a liquid. And I told you, if anyone gives you the composition of a liquid, you are going to assume that it is a mass fraction. Okay, that's usually the assumption. But now they're telling me it's not a mass fraction, it's a mole fraction. All right, so they tell me the feed is made up of propane, C3, butane, C4, and pentane, C5. And I've got 30, 45, and 25%. So let's start drawing my picture. But before we do that, let's just read the rest of it. They say to me, the distillate contains only prop and butane. The bottoms contains only butane and pentane. So you can see the bottoms contains only these two. And then the distillate, or the top, only contains these two. And so you can say all the propane will come out at the top, all of the pentane comes out at the bottom, and then your butane is mixed somewhere in between. Okay. And they also say that the lab analysis of the distillate, so the distillate is the thing that comes out at the top, and that contains 82% carbon on a mass basis. And that's all the information that's been given to me. So let's go ahead and draw a picture. All right. So I'm going to put down my distillation column here. All right. Send in my feed stream and label that F. The distillate that comes out at the top is going to be labeled D, and the bottoms product is labeled B for obvious reasons. All right. Now in your feed stream, you've got 30% propane. So what I'm going to do is I'm going to say 30 mole percent propane. All right. 45% butane. So this is 45 mole percent butane. And then the remaining 25 mole percent will belong to pentane. All right. So we've got prop, but, and pent. That's done. Now let's fill in the distillate. The distillate contains only propane and butane. I'm just going to make a note here. There's only propane and butane at the top. And then they tell me that the bottoms only contains butane and pentane. Okay. I hope this is making sense so far. All right. And the lab analysis of the distillate shows that it contains 82% carbon. I'm just going to make a note here. It's 82 mass percent or weight percent carbon. That's the only thing I know about the distillate. And so the first thing they say to me is 2A, what is the mole percentage of butane in the distillate? So we want to know how much butane is in the distillate. And the only thing I know about the distillate is that it's got 82 weight percent carbon. So as always, if you remember from our previous chemical engineering questions, if someone ever gives you a mole composition, all right, and we'll make a note of it here. Let me just put down 2A, or just A, part A. And what did I want to say? I wanted to say, if someone gives you a mole composition, a good starting point is to start off with a mole basis. All right. So in my feed stream, I'm going to take a basis, or actually over the whole system, sorry. So I'm going to say that my basis is 100 kilomoles per hour of the feed stream. And therefore, if I've got 100 kilomoles per hour coming in, then I know I've got 30 kilomoles per hour of propane, So let's write that down. Therefore, the number of moles of propane in F is equal to 30 kilomoles per hour. The number of moles of butane in F is equal to 45% or 45 kilomoles per hour. And the number of moles of pentane in stream F is equal to 25 kilomoles per hour. Okay, so we've got a good starting point. And let me put this all in a box, right? Because all of these values originate from the fact that I've selected my basis. There we go. All right. I hope you can still hear me fine. I'm just going to adjust the mic. All right, let's continue. So I know what my basis is composed of, but here's an interesting thing to note. I know the number of moles of propane in F, right? But I know that all the propane in F must come out at the top here. And so if I've got 30 moles of propane in the feed, I also need to have 30 moles of propane in the distillate. So I think that's a good starting point, all right? So I'm going to say, therefore, the number of moles of propane in the distillate is equal to the number of moles of propane in stream F, because I know that all the propane comes out at the top, and that is going to equal to 30 kilomoles per hour. Okay, so that's a good observation. Now that I have all of this information, remember I can't work out how much butane is in here, because 45 mole percent, sure, there's 45 kilomoles of butane coming in, but the butane splits between the distillate and the bottoms. So I can't evaluate right now. But let's see if I make use of this 82 weight percent carbon. Let's see if I can use that to calculate the mole percentage of butane in the distillate. So if someone tells me that a stream is 82 weight percent carbon, what does that mean? It means that the mass of carbon over the total mass of the stream, which is stream distillate, is equal to 82%. Mass of carbon over total mass should equal to 82%. And I think you'll agree with me. But now, the only thing I've got is number of moles. So can I write down mass in terms of number of moles? Yeah, sure, I can do that. What is the relationship between mass and moles? Molar mass. So let's go ahead and do that, right? I know that molar mass is equal to number of moles multiplied by molar mass. And then my total moles in D, remember your distillate is composed of the number or the mass of propane plus the mass of butane. It's only propane and butane in the distillate, right? Only propane and butane in the distillate. All the pentane comes out at the bottom. Okay, so let's proceed. So I know that mass of carbon is equal to, okay, let's just write mass of carbon so long. And this is the mass of propane plus the mass of butane is equal to 82%. You agree? I've fundamentally not made any changes to the equation. All right, let's continue. So mass of carbon is the same as number of moles of carbon multiplied by the molar mass of carbon. Oh, sorry. I was thinking ahead. Multiplied by the molar mass of carbon. All over the number of moles of propane multiplied by the molar mass of propane. Okay, so just in case you didn't follow that, I took this mass of propane and I extended it into number of moles multiplied by molar mass, which then ends up here. Okay, plus the number of moles of butane multiplied by the molar mass of butane, and that is still equal to 82%. Okay, so we are making progress. Now remember, I know the number of moles of propane in D, in the distillate. The number of moles of propane in the distillate is equal to 30 kilomoles per hour. So, number of moles of propane. Oh, and let me add this in here. This is number of moles of propane in the distillate, number of moles of butane in the distillate, and this is number of moles of carbon in the distillate. So you might think I'm a bit excessive with my subscripts, but as you start to do more complex systems, it becomes very important that your subscript naming is on point, because it's very easy to make a mistake somewhere along the line. So I know the number of moles of propane in the distillate, right? But I don't know the number of moles of carbon, and I don't know the number of moles of butane. Okay, so we've kind of hit a dead end now. Number of moles of butane, I want to solve for that, right? So I'm not going to try to expand that any further. But number of moles of carbon in the distillate, I want to show you something, right? If I told you for every 1 mole of propane, which is C3H8, for every 1 mole of propane, do you agree that I need 3 moles of carbon atoms? Okay, and for every 1 mole of butane, which is C4H10, do you agree that I need 4 moles worth of carbon atoms? Okay, if you agree with me, then you're in a good place. Okay, just think about that for a second. Now, can I use this logic to expand the number of moles of carbon in the distillate? All right, so let's go for it. All right, number of moles of carbon in the distillate is equal to 3 times the number of moles of propane in the distillate plus 4 times the number of moles of butane in the distillate, and that entire fraction at the top, right, this NC, is multiplied by the molar mass of carbon. So still multiplied by the molar mass of carbon. And this is all over number of moles of propane in the distillate, number of moles of propane in the distillate, multiplied by the molar mass of propane, plus the number of moles of butane in the distillate, multiplied by the molar mass of butane. And again, that is all equal to 82%. So let's have a look at our equation now, right? I know the number of moles of propane in the distillate. I know the molar mass of carbon. I know the number of moles of propane in the distillate and the molar mass of propane. I don't know how many moles of butane we have, but I do know what the molar mass of butane is. So can you see how in this entire equation, the only unknown here is the number of moles of butane in the distillate? And so you can have fun with that, but let me just substitute some values in first. Okay, so that's 3 multiplied by, and then the number of moles is 30, plus 4 times the number of moles of butane in the distillate. Okay, and multiplied by the molar mass of carbon, which is 12. All right, in case my handwriting is a bit untidy, you can just make these square brackets. I think that's a bit more intelligible. All right, the number of moles of propane is 30 times the molar mass of propane, that's C3H8, which is 44 kilograms per kilomole, plus the number of moles of butane in the distillate, which is unknown, and you're going to multiply that by the molar mass of butane, which is 58 kilograms per kilomole, and that's equal to 82%. So if you solve for this, if you've got a programmable calculator, you just put this entire equation in, and your equation will iterate for you until it finds the correct answer, and it will say that the number of moles of butane in the distillate should equal to 5.455 kilomoles per hour. And that's it. You are almost done. Okay, we're almost done with part A. So the question said to me, what was the mole fraction? Let's just go up and double check that. What is the mole percentage or the mole fraction of butane in the distillate? So in the distillate, I'm just going to go up here and I'm just going to actually write out what I have discovered. So in the distillate, I know that the number of moles of propane was 30 kilomoles per hour. And I know that the number of moles of butane came out to be 5.455 kilomoles per hour. So now that I've got these two, I'm just going to put kilomoles per hour and kilomoles per hour. Now that I've got these two, can I find the mole percentage of butane? That's very easy. Okay, so let's do that last step. So I'm going to say, therefore, the mole percentage of butane in the distillate is equal to the number of moles of butane in the distillate divided by the total number of moles in the distillate. So that gives you 5.455 kilomoles per hour divided by 4.455 kilomoles per hour plus the number of moles of propane, which was 30. So 5 over 35 should give you 15.38%. And that is your mole percentage of butane in the distillate. All right, so that is part A. Okay, and remember this 30 kilomoles per hour only applies if my basis of feed is 100 kilograms per hour. Because what you'll see later on is that they tell me that the feed flow rate is 220. And in that case, my basis has now changed. So the only thing applicable is my percentages. But in terms of actual flow rates, for question C, I can't use any of the flow rates I assumed previously. All right. The next thing they say to me is, what is the mole percentage? Oh my goodness. I just realized I calculated the wrong thing. In the distance. No, I didn't. Okay. What is the mole percentage of butane in the bottoms product? So now things get a bit interesting, right? So I know how much butane is entering in the feed stream. I know how much butane is exiting in the distillate stream. But I can therefore work out the number of moles of butane in the bottom stream. And if I know how much butane is in the bottom stream, and I know the composition of the feed stream, do you agree all 25 kilomoles of pentane coming in the feed has to come out as pentane in the bottoms? So once I know the butane and I work out the pentane, I can work out the mole percentage of butane in the bottoms product. And I can work out the entire composition of the bottoms product. So let's go ahead and do that, right? So here we're going to do a mass balance. This is where our mass balance comes in. Okay, so this is part B. And I'm going to say to you, okay, the number of moles of butane in the feed stream is going to equal to the number of moles of butane in the distillate plus the number of moles of butane in the bottoms. So this is unknown, this is known, and this is known. All right. So the number of moles of butane in the feed stream, we said, was 30 kilomoles per hour. No. Sorry. Did I get that right? Butane in feed stream. Let's go up to the picture. How much butane is in the feed stream? 45 mole percent. So there's 45 kilomoles per hour, right? Still using basis of 100 kilomoles per hour feed. Okay, so we've got 45 kilomoles per hour coming in the feed. And how much butane is in the distillate? Let's see. Number of moles of butane in the distillate is 5.455. So that's 5.455 plus the number of moles of butane in the bottoms. And so the number of moles of butane in the bottoms is equal to 39.545 kilomoles per hour. But the question doesn't say to me find the number of moles of butane. It says find the number of moles of, or find the mole percentage of butane. And so I need to know the total number of moles in the bottom stream. I can also say, and I know that the number of moles of pentane in the feed stream must equal to the number of moles of pentane in the bottoms. And why do I say that? Because all the pentane that's entering in the feed stream must exit as pentane in the bottom stream. Remember, no pentane goes into the distillate. And so the number of moles of pentane in F was 25, I believe. I'll go up and double check that now. 25 kilomoles per hour. is equal to the number of moles of pentane in stream B. So let's just go up and check that. How many moles of pentane were in the feed? Yes, 25. Okay. And so do you agree that I now know the entire composition of the bottoms stream? So as my final step, let's go to draw. And I can say, therefore, the mole percentage of butane in the bottoms is equal to the number of moles of butane in the bottoms divided by the total number of moles in the bottoms. So that is equal to, how many moles of butane are in the bottoms again? 39.545. So 39.545 all over 39.545 plus 25. Okay, and this is just the definition of a mole fraction. If you're still a bit confused about how I'm getting this, maybe have a look at the semester test 1 preparation course, where we spent a lot of time calculating mole fractions. But at this point, I'm assuming it's second nature to you. So if you calculate that, you get 61.27%. And that is your answer for part B. And as always, take pride in your answer, present it in a format that the examiner would appreciate. So I'm going to put it in a nice highlighted yellow box. Okay, now let's go into part C. And this is where the question becomes a bit more involved. So for part C, they say to me, all right, now the feed flow rate is 220 kilograms per hour. So you know the mass flow rate. And if you know the mass flow rate and you know the mole composition of the stream, do you agree you can find the number of moles in the feed stream? And if you know the number of moles in the feed stream, then please calculate the bottoms flow rate in kilograms per hour. So I just want to make a note here as well that this bottom stream is composed of 61.27 mole percent butane and then 1 minus 61. I'm not sure what the maths is there. 38 point something. Okay, 38.73. Oops. All right. Okay. This is chemical engineering, not strict mathematics. Okay, so I know the mole composition of the bottom stream, and I can get the flow rate of the feed stream in kilomoles. By the way, okay, they're giving me a mass flow rate, right? Mass kilograms per hour. Why in the world would I want to convert that into moles? Just by the way. Because if I convert that into moles, remember my entire composition is set up as moles. So if I can get the number of moles in this mixture, then I can just say, all right, the number of moles of pentane entering in F is equal to the number of moles of pentane exiting. Boom, we are done. If I'm working with masses, it's going to become a little bit more complex. So let's go ahead and work in our moles. Okay, so for part C, I know that I've been given the information that F is equal to 220 kilograms per hour. Now, how do I turn a mass flow rate into a molar flow rate? And you're already telling me the answer. The relationship between mass and moles is molar mass. So I want to work out the molar mass of the feed stream. So that is equal to the mole fraction of component 1 multiplied by the molar mass of component 1. And if you're not familiar with this calculation, you can watch the videos on ideal gases. This is how we calculate the molar mass of any fluid mixture. Fluid involves liquids and gases. So anytime you've got a fluid mixture, you can use the following equation. It's called the weighted mole fraction equation to calculate the molar mass of your mixture. Okay, plus the mole fraction of component 2 multiplied by the molar mass of component 2 plus the mole fraction of component 3 multiplied by the molar mass of component 3. This is a very important equation. It's a golden equation. Please keep it very safe and do not forget it. So the molar mass of my feed stream is the mole fraction of component 1, which is probably butane or propane. Okay, propane. So it's 30% propane. Let's start there. All right. So it's 30% and the molar mass of propane is 44 kilograms per kilomole. Okay. Plus, then we've got 45 mole percent of butane. and the molar mass for butane is 58 kilograms per kilomole, and the mole fraction for the last component is pentane, so that is 25% of 72 kilograms per kilomole. Okay, and if we calculate all of that, that comes out to be 57,3 kilograms per kilomole. So if I know the molar mass of the feed stream and I know the mass of the feed stream, then we can say, therefore, number of moles in the feed stream is equal to mass of the feed stream divided by molar mass of the feed stream. So that's 220 kilograms per hour divided by 57.3 kilograms per kilomole. And if you do your unit conversions, you end up with 3,839 kilomoles total. So that's the total number of moles in the feed stream. Okay. And I can now say, but I know that 25% of the number of moles in the feed stream is equal to the number of moles of pentane. Why am I singling out pentane? Because I want to work out, let's just go back to the picture. 25% of all the moles in the feed stream belongs to pentane. And if I know how many moles of pentane I have in the feed, then I can tell you how many moles of pentane I have in the bottoms. And then, because I know that pentane makes up 38% of the moles in the bottoms, I can tell you how many moles butane makes up. And then I can quickly convert that into a mass and give you the total mass flow rate of the B stream. I hope this makes sense. Basically what I'm saying is all the pentane entering the feed is equal to all the pentane in the bottoms. So if I can work out the pentane in the feed, I can work out the pentane in the bottoms and use a ratio conversion from there. So let's go down. I know that 25% of all the moles in the feed is equal to the number of moles of pentane in the feed stream. So the number of moles of pentane in the feed stream is equal to 25% of 3.839 kilomoles per hour. And there should also be kilomoles per hour. Okay, so the number of moles of pentane in the feed stream is equal to, and I'm sure I've worked that out here, that's 0.9599. 0.9599 kilomoles per hour. Okay, so I'm going to put this in a box just to keep all our thoughts structured. Okay, and then for our molar mass calculation, I'm going to put all of that in another box. I just use the boxes so that the examiner understands that everything relating to this particular theme is in that box. Everything relating to this particular theme is in this box. Okay? And now I can say, but number of moles of pentane in the feed stream must equal to the number of moles of pentane in the bottom stream. And that's a basic mass balance. And so therefore, 0.9599 kilomoles per hour is equal to the number of moles of pentane in the bottoms. And I know, if we go up, I know that, let's just go up quickly, back to our information, 38.73 mole percent, so 38.73% of all the moles in the bottom stream must belong to pentane. So 38.73% of all the moles in the B stream must equal to the number of moles of pentane. And so, can I solve for the total number of moles in B? Because remember, I don't know this, and I know that the total number of moles of pentane is, number of moles of pentane in the B stream, which is 0.9599. So my total number of moles in the B stream is equal to 0.9599 divided by 38.73%. And so my total number of moles in the B stream is equal to 2.478 kilomoles per hour. All right. And I can say, therefore, the number of moles. So remember, the number of moles of the total number of moles in B is equal to the number of moles of pentane in B in the bottoms plus the number of moles of butane in the bottoms. Okay? So I know the total number of moles in B, 2.478. I know the number of moles of pentane in B is 0.9599. So the only unknown is the number of moles of butane in B. So the number of moles of butane in B is going to equal to 1.519 kilomoles per hour. I just want to take a second and double check that that's right. Yeah, 1.518, 1.519, close enough. Okay, so I know the number of moles of butane in B. So I'm going to put down a final therefore and say the number of moles of pentane in B is equal to 0.9599 kilomoles per hour. And so the mass of pentane in B is equal to the number of moles multiplied by the molar mass. So that's 0.9599 multiplied by the molar mass of pentane. That is 72. Okay. And that should give me 69.113 kilograms per hour. So what I'm going to do is put this in a box. So all of this is my analysis for the number of moles in B. And now I'm doing all my masses. Okay. And I also know that the number of moles of butane in B is equal to 1.519 kilomoles per hour. Let's convert that into a mass. So the mass of butane in B is going to equal to number of moles multiplied by molar mass, which is 1.519 multiplied by the molar mass of butane, which is 58 kilograms per kilomole. And that should give me 88,102 kilograms per hour. Okay? And so, therefore, the total mass in B is equal to the mass of butane in B plus the mass of pentane in B. And that's going to equal to 88,102 kilograms per hour plus 69.113 kilograms per hour. And this comes out to be 157.21 kilograms per hour. And that is the total mass flow rate of the bottom stream. Okay, so let's just, let's just expand this down. And we've got the total mass flow rate of the bottoms. So let's just go back up and see that we've answered the question. They said, what is the bottoms flow rate in kilograms per hour? We have successfully done that. It is here, 157.21. So thank you very much for watching. Thank you for your patience. And let's move on to the next question.